So there's this kind of trifecta of topics that we've covered. First, we went over velocity. And it's like, okay, how do you describe motion? What are vectors? How do you calculate it? What does that mean? And then said, okay, once we got velocity down, we said, okay, well, let's talk about acceleration. Okay, because acceleration is the rate at which your velocity changes. Oh, okay, first we figured out what velocity is, and we figured out, oh, let's talk about how or what's going to happen when velocity changes. Okay, we got that one out. So here's the capstone of this whole thing, and this is forces. So force equals mass times acceleration. So that's that big sign that's hanging up behind you on the wall or in the ceiling. And so what you'll see is, and this is on the lecture notes, and there's Isaac Newton came up with 3 laws of motion. And now, these are laws, these aren't suggestions, okay, these aren't, well, kind of, only if we're can't ask about it on the test, otherwise, not so much, okay? These are laws. So, and we'll go through all of these in time. But the first law is what's known as the law of inertia. Basically what that says is that Mother Nature is a lazy prima donna. So I've got Hank the bowling ball right here, okay? Hank has a lot of stuff. What that means is because Hank has a lot of stuff, it's very difficult to get Hank to move because there's so much stuff in here, okay? Gentlemen, can we close the laptops, please?
Yes, sir.
Thank you. So Hank has a lot of stuff. What that means is that it's hard to get Hank to move, but once Hank gets moving, it's hard to stop Hank. So, like, I'm not going to put my hand out here, love y'all to death, but I'm not going to put my hand out here and as a demonstration, drop the bowling ball and have it land on my hand, okay? Because this is a situation you all intuitively understand that force equals pain, and you're going to go, wow, that's going to hurt a lot, okay? Now, I could take a little 1 Newton apple and drop it on my hand. Oh, okay, hey, not a big deal. Not going to drop Hank. So, this apple, very easy to move back and forth, doesn't have much stuff in it. Hank, not so much, okay? He's got a lot of stuff, hard to get to move, but once you get it moving, it's hard to stop. So this is the second law that's hanging up there that says force equals mass times acceleration, okay? So what that basically says is that, and this intuitively makes sense. So this has not very much mass. Hank has a lot of mass. So if I want the little apple to accelerate, oh, that's easy to do, okay? That doesn't take much force. But if I want to take Hank and make Hank move back and forth, okay, to get that same acceleration, that would require a lot more force. So if you want the same acceleration, as mass goes up, force goes up, okay? And intuitively makes sense. Like, yeah, it's a bowling ball, tough to lift. All right, a lot of force. Okay, cool, a lot of mass. Okay. Now, the third law sounds simple, but it's the one that's most confused. Newton's third law basically says, there's different versions of it, but it basically says that for every action, there is a reaction. Or for every force, there is an equal and opposite force. Or forces are coupled, okay? So the classic example is that I hold up this bowling ball, right? And I drop it. So as soon as I drop it, why does it begin to accelerate? Gravity. Okay, gravity is a force, right? It's kind of cool, right? Kind of important. Okay, gravity's been called the great sculptor of our universe. Because if you didn't have gravity, you wouldn't have stars. If you didn't have the first generations of stars, you wouldn't form carbon, nitrogen, all these other ones that make us us. So like all of the complex atoms that make us up were at one point formed in the death of the first generations of stars. So after the Big Bang, if you didn't have gravity, you would have no hydrogen combining to make helium in a fusion process of stars. Those stars wouldn't collapse, they wouldn't produce carbon, nitrogen, and then you get into supernovas and collisions of those, of dense stars, and that's when you get like iron. So like all the iron that makes up your hemoglobin in your blood was formed in the collapse of very, very dense stars. Okay, that's a whole other process. So when you look at gravity being a force, when I drop this, okay, obviously Hank has a force exerted on him because he begins to accelerate. Because if I drop Hank and there was no gravity, what would Hank do?
Stay there.
Hank would just stay there, okay, right? So this, then you'll hear us talk about this Jedi Stoffellaw thing. Jedi Stoffellaw stands for stop the force and watch. So if I stop applying the force to Hank, and I watch what happens, oh, Hank begins to accelerate. Well, the only way Hank's going to accelerate is if there's an external force acting on Hank, okay? Otherwise, Hank just stays there. So everybody gets it. Okay, here's Hank, all right. And not what I want. So here's Hank. Obviously, gravity is pulling down on Hank, right? Now, here's this strange rock that we're on, okay? Well, by Newton's third law, what happens is that Hank is going to pull up on the Earth with an equal and opposite force, okay? That's it. For every action, there was a reaction. For every force, there was an equal and opposite force. So when I drop Hank, that's pretty obvious. Oh, Hank accelerates. There's the force. Now, why doesn't the Earth accelerate up towards Hank and we kind of like meet in the middle, which would be kind of weird?
Because Hank doesn't have a very big, mass. With mass comes force of gravity, your gravitational force, right?
Yeah.
So he doesn't have a very big mass like the Earth does, so.
So that's a wonderful explanation. So here's the deal. If you look at this in terms of forces, so the force on Hank is going to be the same as the force on the Earth, okay? Earth has a pretty big mass, 5.979 times 10 to the 24th kilograms, okay? Hank has a mass of about 5 kilograms, okay? Slight difference, a little bit. And so the Earth technically will accelerate upwards towards Hank, but it's such a small, minuscule amount that, yes?
I have one question.
Oh, dear Lord.
On this one, wouldn't the initial velocity, like, when you go
No,
just,
you're fine. Perfect. 15, right there. Spot on. Could not be
So-
better.
I don't need those there, or do
No, that's one that goes to 0, and then this one, the
Okay, so
final
that's fine.
velocity when it's.
Okay.
Yeah, you're fine. Okay, thanks. Okay. So, the forces are equal and opposite. The accelerations are not equal and opposite, because that would be really weird. Because if I drop Hank, and the Earth accelerates up towards Hank at the same rate at which Hank accelerates towards the Earth, we would all feel the Earth kind of begin to move up. It's like, oh man, Burkamp, don't drop the bowling ball. It's okay. We'd all accelerate upward. Okay? So, because the Earth has a tremendous amount of mass, it has a tremendous amount of inertia, it's hard to get the Earth to accelerate. And that's okay, right? We are technically accelerating because we're moving around the sun, okay? Because we're changing the direction of our velocity vector. If you shut off gravity, we're kind of screwed because the Earth is going to go in a straight line away from the sun, and we're going to get awfully cold, awfully dark, really, really fast. Okay, so it's okay that we have gravity and it's pulling us around the sun. So, from a historical perspective, you kind of need to understand a little bit of what Newton did. So, one of Newton's famous quotes is that he says, "Because the reason I've seen so far is because I've stood on the shoulders of giants." So Newton did his work after Galileo. And so if you take like this old physics book, or any book for that matter, and you give it a push, every time, what's the book going to do? Keep going or stop?
Stop.
Stop, okay? If I take this golf ball and I drop it and I let it bounce, every time, what's it going to do?
Stop.
It's going to come to a stop. Okay, we could do this lab all day. It's like, what's the lab you did in Burkamp's class? We dropped bowling or golf balls and we saw what happened. Every time, what's going to happen? It's going to stop. The book, every time, what's it going to do? Stop. Okay. Now, there's a Greek philosopher, Aristotle. Aristotle had a huge influence on science and politics and a whole bunch of different things. So, Aristotle's explanation for why the book stops, and in some ways it makes sense. He goes, because the preferred state of motion of that book is at rest. Okay? It wants to be at rest. And so that's why when you push it, every time it's going to come to a stop, because that's what the book wants to do. Okay? Now, if I want to keep the book moving, what do I have to do? I have to keep applying the force, okay? So as soon as I stop applying the force, what's going to happen? It's going to come to a stop. So it's like 6 o'clock on Saturday morning, okay? And Mom knows that Aunt Martha's come to the house. Aunt Martha's pretty judgy, okay? And she doesn't want the house to look messed up because Aunt Martha's going to be judgy and she's going to make snarky little comments to people like, God, you should have seen the house. Okay? So at 6 o'clock on a Saturday morning, your mom needs to make a coffee cake, so she goes, hey, get out of bed. I need you to help me clean. And you're like, really? Because at 6 o'clock on a Saturday morning, what's your preferred state of motion? To be at rest, right? That's 6 o'clock on a Saturday morning. That's your preferred state of motion. If your mom is going to keep you in motion, she has to keep applying a force, okay? So, like, you need dust, you need the vacuum, this whole list of things, okay? And let's say Mom, like, steps out of the room, she's going to the grocery store. You go like, oh, thank God she's gone, okay? So you're going to sit down on the couch and go, like, oh, man, this sucks, okay? Because your mom isn't there to keep applying the force. So you're going to go to your preferred state of motion, which is going to be at rest, okay? And so that made sense for about 2,000 years, okay? From about 400 BC to about 1600 AD, round years, give or take about 5 minutes. We're good for about 2,000 years. And you're going like, why didn't somebody like come up with something new? Well, there was a whole bunch of things they had going on. They had like the plague and, you know, invasions of Vikings and, you know, they had a whole bunch of other stuff to worry about. So Galileo comes along and says, let's think about this. So Galileo says, if I take this book and I push it, yeah, it's going to come to a stop. But if I take a golf ball and give it a push, it rolls quite a ways. Okay? Well, the golf ball does come to a stop, but it takes a long time. So why does the golf ball roll a lot farther than the book does? What's the difference?
Friction.
Friction, okay? So the golf ball doesn't have as much friction. It rolls farther. So Galileo says, let's think this through. If I reduce the amount of friction, the ball rolls farther and farther and farther and farther and farther. So then Galileo says, let's play the what-if game. Galileo says, what if we just eliminate friction altogether? I was like, that's an interesting thought. So if this was the magic frictionless physics book, okay, which would be cool, and I gave that a push, what would the book do? Just keep going, right? So one of the main ideas that I want you to get out of this is the idea that the only reason objects come to rest is because there's a frictional force. If you eliminate the frictional force, you eliminate the force that's going to make that book stop. Okay? So imagine that we take the ultimate field trip. Okay? We're in deep, 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 deep space. Okay? Vacuum of space. And Topher's back there and I'm here, and I'm going to give this book a push to Topher. Okay? So what's the book going to do? There's no gravity, there's no friction. What's the book going to do? Yeah, it's just going to go whoop, straight like this to Topher. Okay? Because the other way that you can have constant velocity is if there's just no other forces acting on it. So if there's no other forces, and I give this book a toss to Topher, that book is just going to keep going. So in our reality, there's two ways that you can maintain motion. You either apply a force to overcome friction, or you just eliminate all the forces, and then it will maintain a constant state of motion. Eliminating all the forces is tough to do, okay? Because there's usually some frictional force. Now, if you think about it, let's say after school today, you're going to drive home, you're going to go south on 119. And let's say the speed limit's 55, and no teenagers ever speed. So you're going to set your cruise control at exactly 55 miles per hour, okay? So basically, at this point, the purpose of that cruise control in your engine is to provide just enough force to keep your car moving at a constant speed. So your engine is just providing all the forces it takes to overcome the frictional force. Same idea here. So whatever force that I have to apply to keep the book moving, is how much frictional force there is. Now, if I put sandpaper on the bottom of this thing, what's going to happen to the amount of force it's going to take? It's going to go up. Oh, there's more frictional force. Okay. So here we are. This is 1600s. Okay. Galileo did his work. Newton reads that, studies it, comes up with his work, the Principia. Okay. And at this point, everybody in the physics community is kind of feeling good. Okay. They're going, okay, hey, we got Newton's laws of motion. All right, that's kind of solid, right? Objects at rest remain at rest. Objects in motion remain at motion. Okay. F equals ma. The beauty of F equals ma is that there's no fractions that go with it. It isn't force equals 1/4 ma or 1/8. Okay, it's just F equals ma. There's no fractions involved. Simple as it could possibly get. Third law sounds cute. Oh, for every action there is a reaction. Oh, everybody's cool with this. And so at the time, they started to come up with this idea of like grand ideas. How can we simplify science into simpler ideas? They said, okay. So they came up with this idea of what they call fundamental forces. So in the universe, there are certain forces that are fundamental. In other words, everything is a manifestation of one of these forces. So the first that they came up with, oddly enough, was gravity. They said, okay, we're going to have 4 fundamental forces. The first one is gravity. This would be really cool if this pin would work, but it's not going to. Gravity. Now, we will spend an entire unit talking about gravity. For now, I'm just going to give you the equation. F equals big G, M1, M2 over distance squared. Okay? So the big G is called the universal gravitational constant. It technically has a numeric value of 6.67 times 10 to the negative 11. Don't worry about that for now. Just realize that it's a number. Okay, it's a really small number. Okay, it's 10 to the negative 11. It's not a very big number. And then you have mass 1, mass 2, and then you have distance squared. So what this means is that the only requirement that you have to have gravity is 2 things. You have to have a mass, you have to have another mass, and if you know the distance between them, you can calculate that gravitational force. Okay? So right now, Taylor Allen is sitting right here, and over there on the wall, there's a fire extinguisher. Okay? Taylor has mass, the fire extinguisher has mass. So right now, there's a certain gravitational attraction between Taylor and that fire extinguisher. Okay? It's not very much. Okay? And we'll eventually calculate, we'll get a numeric value for that. So in the course of this lecture, there's a lot of things I'm going to worry about. But what I'm not going to worry about is that fire extinguisher coming off the wall and starting to float towards Taylor. Okay? There is a gravitational force between Taylor and the fire extinguisher. It's just really small. Okay? But what's important about this is that obviously because you're multiplying 2 masses together, so as the masses get bigger, the gravitational force gets bigger. Okay? So you all are obviously gravitationally attracted to this strange rock that we're on. You have mass. The rock that we're on has mass. Oh, there's a certain gravitational force. Gary the golf ball has mass. Oh, look, there's a force. So for a while, and stay with me here, for a while they thought gravity was magic. No, really? That was the Dark Ages. They had a whole bunch of other things going on. But if you think about this. So let's say that I put this golf ball down, and I let go of it, and then I put my hand up here. And all of a sudden, the golf ball would begin to move up towards my hand. What would you all think? Magic, okay? Burkham's a Jedi, okay? He's a wizard, okay? Or he's a witch that's burning up the stake. Something, okay? Let's just go with magic. Because by that definition of magic, I'm making the golf ball move without an observable force acting on it. Okay, now if I pick it up and lift it, oh, what'd you do? Picked it up. Ball goes up. If I do this and the ball floats up, it's magic. You're a Jedi. Okay? Motion is the same way. Now, but if I hold this ball up and I drop it like this and it falls towards my hand, oh, that's gravity. So if it floats up towards my hand, that's magic. If it falls towards my hand, that's gravity. Both situations, there's no observable force acting on it. Okay? There's not. Oh, that's just gravity. Ah, really? Okay, it's not magic? I don't see any force acting on the golf ball. There's no strings attached. Okay, there's nothing visible. But all of a sudden, oh, the golf ball begins to fall. How is that not magic? So that's why they did away with that idea. But you could see that justification about why they thought it was magic. Because you're making an object move without applying an observable force to it. Okay, so if you look at this concept of this equation, because you're dividing by d squared, what that means is if Taylor gets up and she walks to the other side of him, she goes, you know, Burkamp, that kind of bugs me that I'm attracted to the fire extinguisher. I'm just, not digging it. So Taylor goes, I'm going to go to the other side of the room. Okay? So Taylor gets up and she walks to the other side of the room. What's going to happen to the gravitational attraction between Taylor and the fire extinguisher?
Decrease.
Or decrease. Why? You're getting further away. Mathematically, what are you doing?
You're dividing by a bigger number.
You're dividing by a bigger number. Okay? Okay? And the farther Taylor goes away, the smaller the force is. So what that means is if you were to look at this in terms of a graph, and we'll talk more about this graph a lot later. So if this is your gravitational force and this is distance, so as your distance gets bigger and bigger and bigger, that gravitational force becomes smaller and smaller and smaller. Okay? But because you're multiplying two masses together, this is where it kind of becomes like a self-fulfilling prophecy in terms of star formation. So if you subscribe to the Big Bang, here's a short version. Big Bang happened. You had pure energy. The energy began to spread out. As it spread out, it cools. Here's a good way. It's a poor analogy, but you kind of get the idea. So if you hold your hand in front of your mouth and you blow on your mouth with your mouth open like this, like that, okay? Do that. Okay, how does it feel?
Hot.
Feels hot. Now do the same thing, but pucker your lips. And then blow on it.
Cold.
Now how does it feel?
Cold.
Now it feels colder, okay? Because what you're doing is that as that air expands, it cools. And that's a very, very poor model of what happened in the early universe. So the universe began to expand, and as it expanded, it cooled, okay? So energy began to form into mass. You begin to get protons, electrons, okay? And you began to form hydrogen, which is the simplest element. So if you wanted the simplest possible quiz that ever existed in science, okay, have a quiz on the periodic table right after the Big Bang. Guess what? You have one element, hydrogen. That's it. The easiest quiz you ever had. Now, but because hydrogen has a certain amount of mass, and that's the other kicker, is like, if you look at how our universe played out, what are the three big subatomic particles?
Hydrogen.
Most common subatomic particles. No.
Carbon?
Subatomic.
Oh, electrons, protons, and neutrons.
And neutrons, right? Okay. So one of the big things is like, why did the universe create those particles? Why did the universe? Think about this. What if the universe just created electrons? That's all it had. The universe is a one-trick pony, and we're just going to make electrons.
That'd be kind of fun. Oh, they'd just be like on opposite sides of the universe. Wouldn't that be kind
we
of
wouldn't
funny?
be here having this discussion, right?
Wait, no, they wouldn't. They'd attract to each other. Never mind.
False.
You were right the first time.
Was
I
I?
chose C.
Plus
Okay.
and minus. No, wait. Oh, they're electrons. Never mind. Sorry.
Okay.
We blocked
So if the universe just made electrons, we wouldn't be here having this discussion, right? Because you could never form atoms. You can never form molecules, right?
Yeah.
Same thing is true if the universe just said, hey, I'm a positive kind of person. I'm a positive universe. I'm just going to make protons. Cool. We still wouldn't be here having this discussion. Boring yet, the universe just says, you know, I don't want to mess with this whole positive and negative thing. I'm just going to make neutrons. Okay, cool. The universe just makes neutrons. We won't be here having this discussion because you could never form chains of molecules. So thankfully, the universe makes electrons, protons, and neutrons. Okay? So one of the big debates that happens, and this is one of the great mysteries that we're trying to solve, beyond the fact that like there's this thing called dark matter and dark energy. So it's kind of embarrassing. What we know as matter, okay, depending upon which source you look at, it only makes it between like 5 and 10% of the known mass of the universe, okay? So what we observe, like when you look at the stars and you look at the sun and you look at Jupiter and you look at penguins, okay? That's what we call matter, okay, normal matter. And we think, oh, that's cool, right? That makes up the universe. Cool, okay? It doesn't. Okay, that makes it literally between 5 to 10%. The rest of it is what we call dark matter and dark energy. It's rather embarrassing. It's like we have the vast majority of what's happening in the universe and we have no idea what's going on with it. It's like, what is it? Can you detect it? Nope. Okay, cool. All right. Science is cool. We're missing 90% of the universe. Let's go. Okay, so what we're going to focus on is the 10% that we can deal with. So one of the things that you have to figure out or try to explain is that there's matter and antimatter. So what we're used to dealing with is what we call matter, okay? In typical matter, electrons have a, what charge? Negative charge. Protons have a positive. Okay, so that's what we call matter, okay? If you have antimatter, then instead of electrons, you have positrons. So they're identical to electrons, but they have a positive charge. You have protons, with the exact same characteristics, but those have negative charges, okay? So here's the problem. Like, what's the square root of 4? 2, or negative 2, right? Those are two possible roots. So the universe, when it created, should have produced equal amounts of matter and antimatter. But here's the problem. When matter and antimatter run into each other, they annihilate each other, and it turns back into pure energy. So if the universe had produced equal amounts of matter and antimatter, we wouldn't be here having this discussion, because the electrons would always run into the positrons, and they just annihilate each other, and you couldn't make Oreos or apples or Earth or anything else like that. So one of the things we're trying to settle is like, what tipped the scale? Why did we end up making more matter than antimatter? And so one of the things they're looking into are these tiny, tiny little weird particles called neutrinos. And there's 3 different types of neutrinos. And neutrinos are fascinating because like right now, like if you hold up your thumb, like right now, every second there's about 1 million neutrinos that are streaming through like just your thumb every second. And you're sitting going, oh, I feel that. That's cool. Okay? No, you don't. But they're being kicked out from the sun and from space. And these neutrinos are very, 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 very small. And they don't interact with anything. Okay? They just like pass right through us. And that's okay, because if neutrinos interacted with our particles, that would be really weird. It's like a neutrino, okay? Right? Awkward. So these neutrinos just go right through us. They've been going through you ever since you existed on Earth. It isn't like, oh, did that just start today? No. It's been going on for a long time, okay? There's a whole bunch of knowledge of neutrinos. Matter of fact, one of my former students, Reed Bowles, is working on his doctorate at the University of Indiana studying neutrinos. Okay? So there's a whole branch of science that just deals with neutrinos. So, first fundamental force, gravity. The beauty of gravity is that it's always attractive. Okay, it isn't like you have to wake up in the morning and check the gravity app on your phone. It's like, oh, maybe gravity is repulsive today. Okay, which would be really, really weird. You go to get out of bed and all of a sudden, you know, gravity pushes you up towards the ceiling. Okay, which would be weird. You drop something, oh, gravity goes up. Okay, weird. All right. And gravity doesn't fluctuate much. Okay, it isn't like, oh, it's a strong gravity day today. I was going to play golf. Okay, maybe not. All right. Okay, gravity is a pretty consistent force. Okay, doesn't. Now, in reality, gravity is actually of all the forces, gravity is actually the weakest force, okay? Because it's important, it reaches across infinite distance. So right now, you are obviously attracted to the rock that you're on. You're attracted to that fire extinguisher. You are attracted to the moon. You are attracted to Jupiter. You are attracted to the sun. So the only way you can be in zero gravity is, this is like the ultimate freshman mentality. The only way that you can be in zero gravity is if you are the only thing that exists in the universe. Okay? Literally. If there's anything else that has mass in the universe, you will be gravitationally attracted to that. So you are gravitationally attracted to the most distant electron on the other side of the galaxy. So there is no way you can be in zero gravity, okay? But, so gravity is a one-trick pony, but it's a good trick, okay? It's an attractive force, and it's only attractive. You only have to have mass and a certain distance and calculate that force. So at this point, we're talking, this is like early 1900s, okay, about 100 years ago. If you look at physics books then, you can find gravity, you can find that equation. Okay, cool. So that was the first fundamental force we dealt with. The second one is what they call the electrostatic force. Now, I need that blanket.
Okay.
Not for long, you have it back. So, what we're going to do is we're taking this balloon, so give that
Oh yeah.
a twist. So, I'm going to roll this balloon. Okay? And now when I put my hand up to it, you'll notice that.
Wow. Wow.
Okay. So when I do that, I can very much make that balloon move towards my hand. Okay? It's witchcraft. Pretty much mistake. Okay? Or neat. Okay? So here's the deal. So that begs the question. It's like, huh, that's kind of cool, right? And even if I just, move ahead a little bit of attractive force, okay? And a little bit more dramatic. So obviously there's something going on there, right?
Yes.
And it isn't just one hand, no matter which hand I put up there. It isn't just, oh, it only works with the left hand. No, it works with my right hand as well, okay? So, here's the short version. So, you can think of subatomic particles, protons, electrons, and neutrons, as like dogs, okay? So the electrons are the chihuahuas of the world, okay? They're these little dogs that run around, yip, 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 okay? And they're negatively charged. So if you've ever run around chihuahuas, you know exactly what I'm talking about, okay? They're these annoying little yippy dogs. Hate them to death. Now, then you have the St. Bernards and the German Shepherds, okay? So the St. Bernards are like neutrons. They're these big, lumpy dogs that just kind of lay around going, sad. Okay? Don't do much. They're there. They're important. Everybody loves a good St. Bernard. But they don't do much. They just take up a lot. They provide a lot of mass. Okay? And then you got the German Shepherd. German Shepherds are probably cool, okay? But they're also big. So the German Shepherds and the St. Bernards tend to hang out together in like the nucleus. And then around this, you have these Chihuahuas running around. Okay? They're going yip, 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 yip. Okay, they go running around. So basically what happens is this. When I rubbed the blanket on the balloon took Chihuahuas from the blanket. Okay? So the balloon now has excess Chihuahuas. All right? They're going yip, 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 yip. So my hand is fundamentally neutral. Okay? It's neutral. Because it has a balance between Chihuahuas and the German Shepherds. Okay? Where I'm neutral. So what happens is that when I bring my hand like this, basically what happens, because the Chihuahuas don't like each other. Okay, that's the other story. The Chihuahuas, because they're negatively charged, they don't like each other. So when I put my hand like this, the Chihuahuas that make up my hand go, we're out of here, because they don't like the Chihuahuas on the balloon. So the Chihuahuas in my hand go running away. Now, the St. Bernards and the German Shepherds, they're like, just chill out, okay? Because the German Shepherds, which are positively charged, like the Chihuahuas, because they're negatively charged, and opposite charges attract. So when I put my hand here, that little bit of surface on my hand, the Chihuahuas have gone away. they've migrated away. Because they're like, screw this, we're out of here. Whew, we're out. Okay? The German Shepherds are left behind. They're positively charged. So when I put my hand here, the Chihuahuas are attracted to the St. Bernard, or to the German Shepherds in my hand. And that's why it begins to move in this direction. Now, if I do this, let me charge this one. So migrate some Chihuahuas. That's cool. Now when I try and put them together, they are going to repel each other. Why?
Because they
Both
both
have
have
chihuahuas.
Yeah,
Extra chihuahuas.
they both are overloaded with Chihuahuas. So the
Imagine you
Chihuahuas
answer.
on the balloons don't like each other. Because they're going, yeah, you're Chihuahuas, we're Chihuahuas, we don't like each other, let's go away. Now, that's actually a horribly complex, if you look at the physics behind what's actually taking place, because it's actually the exchange of photons. So all of the fundamental forces have what's called a carrier force on it. So they think gravity is kind of clever. I think gravity might be carried by a force called a graviton, which sounds kind of cool. It's like, oh, gravitons, I feel it, okay? It's a good idea. We haven't been able to find any yet. But we do know that the electrostatic force is carried by photons. So what's happening is that same kind of photons that are like producing light are what's actually making that happen. Okay, so stop that camera, and we need to move to the back of the room. So what this is known as a Vandergraft Generator. So it has a rubber band that goes around, and what this does is that it basically does what I did with the balloon and the blanket, just on steroids, okay? So when you turn this on, that moves, and it builds up an excess electron charge on there. And you can actually hear the sparks forming. And if you touch it, okay, you get shocked because you have an excess of electrons. So what I'm going to do is I'm going to take this and put this up here, and we'll turn this on.
You touch
Wow.
Now, why did it do that?
Yeah. I don't know.
Chihuahuas.
What about Chihuahuas?
They don't like each other.
Okay, so what we're doing is that we're building up excess Chihuahuas, right? And the Chihuahuas don't like each other. So they want to get as far away from each other as they can. Now, if I take my hand, I kind of do this Jedi trick, right? Because, look, what's happening is that my hands, Chihuahuas, don't like those Chihuahuas, and they move away. But if I do this, and quickly touch it, okay, then I discharge those electrons because I give those electrons a place to go. We're back on, we're back.
Wait, so how are they going through to the
Okay.
thing? Is it going through the,
Yeah, it's
like
going
the whole
through that
entire thing,
base.
all the matter and stuff?
Yes, going up there, because the Chihuahuas are trying to get as far away from each other as they can.
So it's only if you like touch it, right? Something's touching it. It
Yes.
can't go through air.
Well, it will go through a little bit of air, because that's why when I stop it, Mother Nature doesn't like that high a concentration, so it's actually, those electrons are actually being dispersed into the air. But when I touch it, I give it a much easier conduit, and those electrons are now flowing over my skin. So if I put a few pieces of paper up here, okay?
Wow.
Ooh, okay. Thank you very much. So when I do that, why do bits of paper go flying off? Chihuahuas. Okay, what's the right answer? Chihuahuas, right? It's building up Chihuahuas. The Chihuahuas don't like each other. They say, we're out of here. Now, if we really want to generate a lot of Chihuahuas, okay, this is called a Tesla coil, okay?
I have a lot in my house.
And you can see that this, so,
see the shot.
Maggie, can you shut off those, hit that switch and turn off these backlights,
That's
please?
so cool.
Hashtag lit.
Wow.
Yeah, just hit the very bottom. It should. There we go. That's nice. Okay. So now when I do this,
Wow.
so what I'm doing,
Wait, I can zoom in.
at the end of this, I'm creating a tremendous amount of chihuahuas. And the chihuahuas are looking for a place to go, and they go into the surface of that. Now, if I hold this fluorescent bulb and put the end of it up here,
Wait, do it again.
okay?
Oh, it lights it up.
So even if I don't touch it, what do you notice what happens to the fluorescent bulb?
It flickers.
It lights up. Now, if I actually touch it, okay,
Whoa!
It's like that movie you'd put like
you'll
a,
notice
what's his name?
that it generally really doesn't go past my hand.
Zeus?
Zeus with
Because
his
what
lightning.
happens is the chihuahuas hit my hand, they go, oh, that's an easier way out. Now, if I overload it and actually touch it, so if I just bring it close, notice it doesn't go past my hand. If I actually touch it, then it will go a little bit past my hand just because I'm overloading it so much. But if I'm just like this, so what's happening is that there's so many chihuahuas, and that's being transmitted through the air to that bulb. The bulb chihuahuas are going, oh, this is cool, right? And then they gain energy and they start to emit light. So,
Chihuahua.
chihuahuas. It's all about the chihuahuas.
So what are tests that can the chihuahuas?
Yeah.
Oh yeah.
What's your choice? Chihuahuas. Okay.
Wow.
Now, let's say that you need to pick up little bits of matter. So, please. Please. So I'm taking this, turn the plug, and move that over. Magic. Okay? So, why are they attracted?
Chihuahuas.
So basically, the balloon is just like what happened with my hand. So the bits of paper are like my hand. So one side of the paper has the chihuahuas that went away from it. You leave the German Shepherds on the other side. So the German Shepherd side of the paper is attracted. The Chihuahua end is repulsed. Now, in an extreme case, what you can do is, so I've got my pen. Oh, come on. Somebody's got to get going.
Wow.
Yeah, that was right. Woo! Okay. So, this is a situation we're calling action at a distance. So I can make the can roll without actually touching the can. So what's happening?
Chihuahuas.
What about the chihuahuas?
They're attracted. No. They're moving away from the protons inside of that.
The can are moving away, right?
Yeah.
That leaves
The positive side on the surface. Oh yeah.
the German Shepherds. live
Sorry,
on the
I
positive
couldn't
side, right? So then, basically, what we're doing is we're creating. Come on, let's go from here.
I hate dogs.
We're creating a torque. Come back.
He was so cute last night. He stopped by
Hand
us when
down.
I was in work and he was making me
I
bread.
can do chihuahuas.
Yeah, we should delay all of my homework. Didn't know he looked so cute.
Come on. So what's happening is that you're basically creating a situation. Oh, come on. Don't let me down, physics. So you can make that roll because what's happening is that at that region, the Chihuahuas are run away, the Saint Bernard or the German Shepherds are left behind. They're attracted to Chihuahuas, but you're always changing that location as that can rolls around. Got it? Good? Grand? Okay, back we go. First time around.
Hey guys, this is Maggie.
The vlog. Eric would have been able to do that.
I hate my pen.
You should get a new one.
Well,
Oh dear.
Did you ask it nicely if it was
nope. I've tried talking to it. I've tried yelling at it.
Maybe
Nope.
you hurt its feelings.
That's not real fair. Okay, so Here's what happens if you look at the electrostatic force. I would never expect you to do any calculations with this. But if you notice that K, that's just a number. Similar type of form that we had for the gravitational calculation, okay? We had big G, that was just a number. Big K, that's just a number. Then you have Q1 and Q2. Q is referring to the charges, okay? So that would be like the charge on this balloon and the charge on the other balloon, okay? Measured in coulombs. Coulombs are a fundamental measurement of the universe. And notice also that is divided by d squared. That's why when I brought my hand closer, the attractive force became greater. And that's why, like, I couldn't make the can roll if I had the balloon way up high. But if I brought that balloon closer, then I could make the can roll. So this is a classic situation where it's called an inverse square law. Gravity is the same thing. If you double the distance, the force goes down by a factor of 4 because it's like d squared. If you cut the distance in half, it goes up by a factor of 4. So one of the things in physics is they wanted what's called a unification theory, because they said, okay, gravity is big G m1 m2 over d squared. Electrostatic force, which is charged particles, is a similar type thing. It's kq1 q2 over d squared. They said, is there a way we can unify these? And they've tried for the past 100 years, and it's been an epic failure, okay? Because on a quantum level, gravity fails. It's horrible, okay? It's a train wreck. The two are basically, gravity and quantum mechanics you cannot merge the two together. So it's just not going to happen. So early 1900s, everybody was cool. You had gravity, you had the electrostatic force. Electrostatic force, you kind of understood what it was. We had some equations to describe it, and it was cool. Now, the electrostatic force is by far and away the most diverse force. That the electrostatic force is what creates friction. So it's supposed to be like 57 degrees tomorrow morning, okay? It's like, wow, that's going to be cold. If you're outside and you're going, oh, it's cold, you're going to rub your hands together, okay? When you rub your hands together, that's friction. Friction generates thermal energy. That's the electrostatic force. Light comes from the electrostatic force. If you want to make toast, that's the electrostatic force. If you want to hold your pencil and write, okay, that's the electrostatic force. Because if you think about it, one of the cool things about when you write with a pencil, on an atomic level, it's pretty cool. So you have graphite. So we have figured out how to make the particles that make up the pencil stick together, okay? Otherwise, it would be a liquid, okay? But it's a solid. We make them stick together. But then, when you write on that piece of paper, that transfers from the pencil to the paper. So on an atomic level, you are tearing apart your graphite, and it's sticking to the paper. It's like, that's kind of cool. And it isn't like you pick up your paper and you shake it, and then all of the graphite falls off. That would be horrible. It's like, Burkamp, I had my test done, I picked it up, and it all fell off. I don't know what happened, okay? No, okay, it sticks there. So, and it sticks to the paper because the attraction to the paper is stronger than the attraction to the other graphite, okay? Otherwise, it wouldn't write. Don't try and write with a diamond. Diamond is basically carbon atoms, the same thing as graphite is. You take your diamond and go, I'll write my test in diamonds. That's not going to end well, okay? Because you're not going to tear that apart. So, you have no homework for the weekend, okay? On Monday, we will continue this discussion and enjoy your 4 days. If either of you want to come up and if you want to retake that test, if you want to come up with your old test during teacher conferences and get that done while it's fresh in your mind, that's cool. I'll be bored out of my mind most likely, so feel free to do that. Okay.